Hello guys, I am Varun and today me and my friends are going to talk about FM radio receivers. Since we are all very well acquainted with the radio, let us dive right into its deep mysterious working. A radio receiver receives its input from an antenna, using electronic filters to separate unwanted radio signals for all other signals picked up by the antenna, amplifies it to a level suitable for further processing, and finally converts through demodulation and decoding the signal into a form usable for the consumer, such as sound, digital data, information, etc. In radio communication, information such as sound is converted by a transducer such as a microphone to an electric signal which modulates the radio wave sent from a transmitter. A receiver intercepts the radio wave and extracts the information varying electronic signal which is converted back using another transducer such as a speaker. Frequency modulation, on the other hand, varies the frequency of the carrier. The instantaneous frequency of the carrier is directly proportional to the instantaneous value of the input signal. FM has the capture effect, whereby a receiver only receives the strongest signal, even when others are present.
So, that was all about frequency modulation. Now, let us talk about a very simple radio receiver known as a crystal radio receiver. The special thing about crystal radio receiver is that it needs no power source and it sustains solely from the power of radio waves registered by a wire antenna. It gets its name from its most important component, known as a crystal detector, which nowadays we call as a diode. Because they don't have an external power source to amplify the weak radio signals. Thus, crystal radios produce rather weak sound and can only receive stations within a limited range. So, that was about crystal radio receiver, which is a very simple radio receiver and was used in earlier times. But today, we are going to talk about a much better and modern version of radio receivers, a heterodyne receiver. Now, any basic receiver must fulfill some requirements. In general, radio receiver must work with AM and FM signals, but in this system, receiver is chosen which will work with FM signals. Must be able to tune and amplify the desired radio station. It should also filter out all the other radio stations except the one which is desired. Also, irrespective of the carrier frequency, the demodulator of the radio receiver has to work with all radio stations.
The antenna collects the radio signal. The tuned RF stage with optional RF amplifier provides some initial selectivity. It may also serve to prevent strong out-of-passband signals from saturating the initial amplifier. A local oscillator provides the mixing frequency. It is usually a variable frequency oscillator which is used to tune the receiver to different stations. The frequency mixer does the actual heterodyning.
Or the radio technique to create a new frequency by combining or mixing two other frequencies.
It gives the super heterodyne its name. It changes the incoming radio frequency signal to a higher or lower fixed intermediate frequency. The IF bandpass filter and amplifier supply most of the gain and the narrow band filtering for the radio. The demodulator extracts the audio or other modulation from the IF radio frequency. The extracted signal is then amplified by the audio amplifier. Now let's consider each part of a receiver circuit in a bit more detail. The output of the antenna is very small, often in the range of a few microvolts. Hence, the signal from the antenna is tuned up by the RF filter and amplified by the RF amplifier. The RF filter is a subsystem for receiving radio frequency transmissions and to convert selected carrier wave frequency along with the associated bandwidth into a fixed frequency which is suitable for further processing. Now let's talk about the mixer. The actual radio frequency is converted into an intermediate frequency. In transmission or reception process, carrier frequency is shifted to a frequency called as intermediate frequency, which is created using a local oscillator and mixing the carrier signal through the heterodyning process. The main reason for converting the RF to IF is due to poor performance of signal processing circuitry and failure of active devices such as transistors to deliver much amplification. Now let's talk about the IF filter and amplifier. The heterodyning process carried out by the local oscillator also introduces a number of unwanted mixed products or undesired frequencies. The main function of the IF filter or intermediate frequency filter is to eliminate these unwanted frequencies other than intermediate frequency by filtering. The stages of an intermediate frequency amplifier are tuned to a fixed frequency that does not change as the receiving frequency changes. The fixed frequency simplifies optimization of the IF amplifier. Finally, let's come on to the demodulator. The received signal is now processed by the demodulator stage where the audio signal is recovered and then further amplified. A trivial AM demodulation requires a simple rectification of the RF signal and a simple RC low pass filter to remove remnants of the intermediate frequency. However, FM signals as we consider them are more complicated. They require devices such as a discriminator, ratio detector or a phase lock loop than that of AM transmitters. So, an audio amplifier is used for amplifying the output to generate a clear, loud, audible output.
Now, that was all well and good. Now we understand the block diagram of a radio receiver circuit. But we need to know how does that circuit look in real life. So, that is how a real circuit looks like. This circled region of the circuit is the tuning region. It helps us to tune to a particular station. Now, before I tell you how the concept works, I am going to tell you about how do we actually tune. If we advance the potentiometer VR1 slowly towards the end of track, connected to the battery positive, then suddenly a slight increase in background noise will be heard at about halfway point, which indicates onset of oscillation. After that, potentiometer VR1 must be backed off slowly until the oscillation just stops for tuning in some stations. Then by adjusting VC2 at high frequency around 108 MHz and by stretching or squeezing the turns of our coil L1 slightly at the end at around 87 MHz, we can obtain the correct frequency range of 87 MHz to 108 MHz. Frequency spectrum over here can be shared by different radio stations through FM modulations. So now, a very much important question. How do we actually tune? In order to tune the receiver to a particular station, the frequency of the local oscillator is controlled by the tuning knob. Tuning of the local oscillator and the RF stage may use a variable capacitor or a varicap diode. Now, tuning is essentially setting a circuit to resonate at the desired channel frequency. Near the frequency, something like this happens. Yeah, when we are near a desired frequency, our current amplitude increases very sharply. Now, now this shows our average power versus our frequency. Our average power increases by huge amount near our desired frequency. Here we see that is delta W, that is the width gap. Now we have a quality factor which is W naught upon delta W, that is a required frequency of the station upon our width gap. Now, sinusoidally driven resonators have higher quality factors and thus resonate with greater amplitudes at the resonant frequency but have a smaller range of frequencies around that frequency for which they resonate. The range of frequencies for which the oscillator resonates is called the bandwidth. Thus, a high quality tuned circuit in a radio receiver would be more difficult to tune but would have more selectivity. It would do a better job of filtering out signals from other stations that lie nearby on the spectrum. High, high Q oscillators oscillate with a smaller range of frequencies and are more stable.
We'll now discuss the various other components of the circuit. VC1 and VC2 are variable capacitances. VC2 is a special type of capacitance known as trigger capacitance. This capacitance is only changed while calibration or recalibration of instrument during manufacture or repair. On the other hand, VC1 is a variable capacitor which the user can change by turning the knob on the receiver circuit. When the user changes the capacitance of the capacitor, he changes the resonance frequency of the circuit. As a result, when the antenna receives a signal with a frequency near to 1 by 2 pi times root LC, when L is the inductance and C is the capacitance of the circuit, The output signal has a larger amplitude when compared to other frequency signals. Thus, this part, coupled with the transistor, can act as a selective amplifier for that band of frequencies. This LCR circuit acts as a filter and allows only certain frequencies of signal to pass through. When these frequencies are in the radio wave part of the spectrum, this LCR circuit is known as a radio frequency filter or an RF filter. These transistors are properly biased through resistors to act as amplifiers. When they receive these signals from the LCR circuit, they selectively amplify the radio frequency part of the signal and thus get their name as radio frequency or RF amplifiers. This is a demodulating circuit. This circuit converts the frequency modulated signal into the output signal, that is the voice that we want to hear. Now this voice is transferred to the headphones or speakers so that we can hear the voice that we wanted to receive through the radio. Now, in order to tune to a particular radio station such as 93.5 Red FM, the user needs to change the value of the capacitance VC1 so that the resonance frequency of the LCR circuit becomes equal to the frequency of the station, that is 93.5 MHz in case of the Red FM. When this happens, the user will be able to hear the Red FM bajate raho.